Welcome to the Anchors 1 module of our series. In this video, we'll cover top rope anchor basics. The context of our anchors will be in situations where you have hike to top access to the climb. Some examples in Wisconsin include the climbing areas at Governor Dodge State Park or Devil's Lake State Park. In the Anchors 1 module, we'll focus on two genres of anchors. The first will be top rope anchors rigged on bolts, where the bolts are close to the edge of the cliff. Then we'll shift to top rope anchors that rely on rigging natural features away from the cliff and extending the anchor over the edge. Methods commonly used in areas like Devil's Lake State Park that hold a steadfast tradition of climbing without bolts.
Let's first dive into bolted anchors to get a core understanding of top rope anchor anatomy. There are a wide range of anchors that we can rig on bolts, but we'll discuss just two in this video: the pre-equalized overhand and the quad. To rig the pre-equalized overhand anchor, we'll use a 120 centimeter sewn sling. A 7mm cord tied into a closed loop works just as well. In this case, we have a double fisherman's bend to tie our cord into a cordelette. Cordelette has some advantages over slings. It's cheaper, you can more easily customize the length, and knots are generally easier to untie. Slings, on the other hand, are more lightweight and compact, but the knots can get welded shut, especially in Dyneema slings. Clip a single strand of your material to both bolts. Pull down on the center of the loop to join both strands together. Orient these strands in the direction of expected pull and tie an overhand knot. Take care to keep the bar tack or joining knot away from the overhand or other points of stress. The two strands of this knot make up the master point. Clip two locking carabiners opposite and opposed and thread the rope through. Your system is now ready to top rope, but let's dig into the details. For all top rope anchors, there's an ingredients list of best practices that we use to check off the anchor before we leave it unobserved. We'll use the acronym SERENE as our checklist, but there are other similar versions out there. The S in SERENE stands for solid or strong, referring to the integrity of the components and attachment points of the anchor. They all must be plenty adequate to sustain the force loads anticipated for your climbing scenario. At worst case, we're loading the anchor with only a few kilonewtons in a top rope setting. Our anchor here is built using this well-kept 120 centimeter nylon sling with no visible damage or blemishes and a minimum breaking strength of 22 kilonewtons. The overhand knot reduces the material strength by about 25 to 50%. All of the carabiners here are UIAA certified with a locked axial load minimum breaking strength of 22 to 25 kilonewtons. Clearly, all of our material choices are plenty sufficient for a top rope scenario. The most questionable component in any bolted anchor are the bolts themselves. We must be diligent and inspect them for rust, sharp edges, movement, and most importantly, the quality of the rock medium that they're connected to. Stainless steel expansion bolts and glue-ins are the modern standard for bolts. It's a good idea to check Mountain Project for the age and size of the bolts, and for any other red flags that might show up in the comments or descriptions of the route.
The E in SERENE is equalized. Attachment systems should distribute the load from the master point to the anchoring components in an appropriate manner. Nothing can be perfectly equalized, but it's important that each leg of the anchor has functional tension. Here, we've pre-tied our overhand knot in the intended direction of pull, allowing the load to be well distributed on the bolts when there's a force applied to the anchor. If the direction of pull changes, this anchor is not well equalized, a major drawback to this design. If such a scenario is expected, for example a traverse, one should consider a self-equalizing anchor, which we'll discuss later in this video. The R in serene is redundant. Any one material in the anchor can be removed or cut, and the anchor will not fail. In our anchor, we can remove a bolt, any one of the carabiners, or a single strand of the sling. Any one of these removals does not completely compromise the anchor's integrity, and it is still sufficiently strong for our climbing scenario. The E stands for efficient. That is, the anchor accomplishes all of its required principles without extraneous and unnecessary systems. The last part of serene is no extensions. For this, if an individual part of the anchor fails, extensions of the master point are limited to reduce shock load on remaining components. If we remove a bolt or carabiner, the master point doesn't extend in this anchor. Anchors that self-equalize can extend in the event of a component failure, and we need to be mindful of this in order to reduce the shock load to the anchor.
Next, we'll build a different anchor, the quad. We'll use a 240 centimeter sling, but we can also use our 20-foot cordelette. We'll start by folding our material in half, creating 4 overlapping strands. Clip one end of the strands to the bolt and tie an overhand knot about 12 inches down from the bolt. Tie another overhand knot about 8 inches further down and clip this other end of the sling to the other bolt. We're now left with 4 strands in between these overhand knots, which we'll use for our master point. Clip 1 locking carabiner on 3 of the 4 strands. Then clip the other locking carabiner, opposite and opposed, to a different set of 3 strands. Thread your rope through both these lockers and you're ready to go. Now for serene. As discussed, all the components are strong and solid. Both the bolts are in good condition, the carabiners are all strong, and the Dyneema sling is rated for 22 kilonewtons, plenty sufficient even with the knots in play. For equalized, we see a major benefit of the quad. The master point can self-adjust as the direction of pull changes, keeping functional tension on each anchor leg and sharing the load more equally between the bolts. This is a great advantage of this anchor if we expect the direction of pull to change throughout our climbing scenario. Redundant follows suit. Any carabiner or single strand can be removed in this anchor without anchor failure. Efficient also applies here. There are no extraneous systems in our anchor. Self-equalizing anchors do allow for extension if an anchor leg fails. In this scenario, the master point carabiners slide down to the overhand knot, shock loading the other leg. We can reduce the shock load by tying the load-limiting knots close to the master point. There's a trade-off to self-equalizing anchors. The greater the ability to adjust to variable directions of pull, the more extension and risk of shock loading the system. Armed now with a core understanding of anchor fundamentals, we can begin to discuss anchors in the context of climbing areas without bolts, and where the master point needs to be greatly extended over the edge of a cliff. These types of anchors are common in places like Devil's Lake State Park, where there is an abundance of natural features behind the cliff to rig our anchors. However, before we can build these anchors, we need to learn how to manage our risk near the edge of the cliff using personal tethers. Since we'll build all of our extended anchors using static line, like this 30-meter coil of Mammut 10.5mm performance static, we'll rig our personal tethers in the context of this material. Personal tethers are connections to the earth that we attach ourselves to as we operate near the cliff edge. Since our top rope anchor master points will be constructed over the edge, we'll be rigging near serious fall potential, possibly even in 4th or 5th class terrain. So we'll rig tethers to manage our risk as we access our master point.
We'll rig our tether by fixing our static rope to a point of natural protection. Suitable candidates for natural protection include trees that are 6 inches in diameter or larger, alive and well-rooted. Our boulders that are mini fridge sized or larger, either well connected to the earth or freestanding with no ability to wobble. In this case, we'll begin by wrapping our static line around this large oak tree and tying a bowline backed up with a double fisherman. Since this tree is a few feet in diameter, it is plenty sufficient for a full strength anchor. The most rudimentary tethering system is to tie a bite knot or an alpine butterfly, approximating the location of the knot to be near the edge where you will operate, then attaching your PAS to the knot. This method is simple, but the major drawback is that it offers little adjustability and has the potential for shock loading in the event of a fall.
Adjustable tethers are sometimes preferred. The first adjustable tether we'll discuss begins by tying a clem heist with a 120 centimeter nylon sling and attaching it to your belay loop with a lock and carabiner. Nylon is much better than Dyneema at biting the rope, and it's always good to give it a few tugs to ensure the number of wraps is sufficient. Knots in the sling allow for different attachment points to your belay loop. The key is to have the clem heist in arm's reach, as the friction hitch will only slide when the clem heist is grabbed. Alternatively, a prusik loop or hollow block can be rigged to the static cord with a friction hitch, which you can then attach with your pass. If entering high consequence terrain with your friction hitch tether, back this up with a clove hitch to your belay loop whenever the static rope isn't already part of a larger system.
Another way to rig an adjustable tether is to use an assisted braking device like this Petzl gree-gree. Attach the gree-gree with the climber side of the belay device on the side of the rope that's anchored. You can use the handle to lower yourself into your working area. If you ever want to go hands-free, just tie an overhand on a bite immediately behind the gree-gree on the brake strand, and you can begin to work on your anchor. We'll see the pros and cons of all these different tethering systems as we begin to build various anchors.
Now equipped with appropriate tethers for working at the edge, let's build our first natural anchor at Devil's Lake, called the V anchor. Begin by rigging your personal tether line onto an appropriate anchor point with your static rope. This tethering point will be one of the anchor legs in our construction, so it will be advantageous to use a friction hitch tether in this scenario. Move towards the edge and locate the master point. scan a V with a 45-degree sweep behind the master point location and identify a suitable place for additional natural protection.
Attach the other end of your static rope to the anchor point identified in your sweep with a bowline and a backup. This will be the second leg of our anchor. From here, return to the master point and estimate about a 3-foot bight of rope over the edge. Then, tie a double overhand on a bight, also known as a BHK or big huge knot. Pass the knot through its tail and attach your master point lockers, opposite and opposed. We'll use the tethering line as our second leg, since it lies within our V-scan. However, we'll need to take out the extra rope from the system to equalize this leg. To do so, tie an overhand on a bight near the master point and attach a locking carabiner. Then, tie a clove hitch in tension, removing the excess rope from the system. Adjust the clove hitch as needed until there is functional tension on this leg and the load on the master point is shared between both legs. Now you can see why this is called a V anchor, as the two legs form a V shape to the master point. Finally, attach the middle mark of your rope to the master point lockers and begin lowering the rope down the climb. Scan the ground and call rope before lowering the ends over the cliff. The weight of the rope should add some tension at the master point, allowing us to check our equalization. Feel the tension on each leg and adjust the clove hitch appropriately, either adding or removing length to the second leg to properly equalize at the master point. We now have our first top rope anchor built, ready to climb, rigged using natural protection.
Now we'll discuss a variant to the V anchor called the N anchor. We begin as before by rigging a personal tether to a fixed point far from the edge. However, now we'll rig two independent fixed lines of our static rope coming from the central fixed point. One way to do this is to simply tie a bowline on a bight around the tree. Alternatively, if we wish to save material in our static line, we can sling the tree with additional soft goods such as cordelette or webbing. Then we tie an overhand knot with a locking carabiner and attach it to our static line with a bight knot. Either strategy gives us two independent lines. One will be our tether and the other will be a leg to our anchor. Since these lines are independent, it's best to use our gree-gree here to work near the edge.
Continue with the usual construction. Find a second leg of your anchor within a roughly 45-degree V-scan and fix the other end of your static line to that point. tie your BHK master point and adjust the last leg, all while staying on tether. We are left with 3 lines forming an N shape. You can see how this method is cleaner as it keeps our tether out of the system. However, N anchors require more material, so this configuration might not be possible depending on the length of your static line and the distance of your anchor points from the edge. We've built several anchors in the course of this video, and now is a good time to discuss a few final considerations with our top rope anchors. The 2 legs of an anchor form a critical angle at the master point knot. When this angle is more obtuse, our anchor is more stable, meaning that the master point is less likely to shift when loaded from various directions. However, wider angles increase the forces on each of the individual anchor components. Rigging your anchor legs with more acute angle decreases the master point stability as well as the forces on each of the anchor legs. With these more acute angles, the total force on the master point is closer to the sum of the forces on the legs. Staying around 45 degrees at the master point knot is a good compromise between these 2 competing effects of stability and force. But it is important to analyze the specific situation when considering these critical angles. One last consideration is protecting our soft anchor materials from abrasion and cutting. One of the major benefits to this 10.5mm static line is its resilience. However, we should always inspect the surfaces that come into contact with our soft goods. In particular, look for sharp edges that might rub a strand of the anchor, which could damage or cut the material. We can mitigate damage by padding these contact points with abrasion-resistant material, such as the Petzl Protec, fire hose, old carpet or shopping bags, or even the leftover coil of our anchoring material.
In this video, we've covered the fundamentals for top rope anchors. Use the core concepts we've discussed, such as serene, to apply to all of your top rope anchor constructions moving forward. The pre-equalized overhand and quad anchors explored in this video can suffice for almost any top rope anchor scenario with bolts. However, there are many other types of similar anchor constructions out there with nuanced pros and cons. So be open to learning other systems as you build up your anchoring toolkit. In the Anchors 2 video, we'll expand our V and N systems that extend the anchor over a cliff edge to incorporate the use of traditional climbing protection. Finally, as you begin building these anchors, seek out double checks and feedback from peers and mentors as you become more familiar with these systems.